Hilbert space is a complete inner product space. This means it is a vector space that has an inner product which allows us to define a norm. Additionally, the space is complete with respect to that norm, meaning every Cauchy sequence in the space converges to a limit within the space. In other words, a Hilbert space H is a vector space equipped with an inner product, denoted as the operation that takes two vectors and returns a scalar, such that the norm induced by this inner product, defined as the square root of the inner product of a vector with itself, makes H a complete metric space. This means that every Cauchy sequence in H, which is a sequence where the elements become arbitrarily close to each other as the sequence progresses, converges to a limit that is also within H. One of the most well-known examples is the space of square integrable functions, often referred to as L-squared spaces. In these spaces, the functions f satisfy the condition that the integral of the absolute value of fx squared with respect to x is finite. The inner product in this space is defined as the integral of fx multiplied by the complex conjugate of gx with respect to x. Another important example is the space of square summable sequences, denoted as L2 spaces. Here, the sequences represented as A equals the set of a sub n satisfy the condition that the sum of the absolute squares of a sub n from n equals 1 to infinity is finite. The inner product for sequences is defined as the sum of the product of a sub n and the complex conjugate of b sub n from n equals 1 to infinity. In a Hilbert space, two vectors u and v are orthogonal if their inner product equals 0. This idea is essential for understanding projections. The projection of a vector u onto a vector v is calculated by taking the inner product of u and v, dividing it by the inner product of v with itself, and then multiplying the result by the vector v. Projections are essential in various applications, including optimization problems and signal processing, where they help in approximating solutions and filtering data. A Hilbert space can have a basis, which is a collection of vectors that can be used to represent every element in the space through combinations. And these vectors are not dependent on each other in a linear way. Infinite-dimensional Hilbert spaces are especially fascinating because they enable the representation of functions and sequences that cannot be described using a finite number of terms. For example, the Fourier series is a way to represent a function as a combination of sine and cosine functions. These sine and cosine functions serve as the building blocks for describing functions that are square integrable over a specific interval. Operators on Hilbert spaces are functions that take elements from the space and map them to other elements within the same space. These operators can be linear, which means they maintain the properties of vector addition and scalar multiplication. An important class of operators is the self-adjoint operators, which satisfy the condition that the inner product of t applied to x and y is equal to the inner product of x and t applied to y for all vectors x and y in the space. These operators have real eigenvalues and eigenvectors that are orthogonal to each other, making them crucial in quantum mechanics and differential equations.